Okay, so you should be able to see my presentation now, full screen. And this is the introduction repetition. So it's about elasticity. I go quickly through. I just want to remind you which keywords you should know. I will not explain everything in detail unless you ask me. Okay, so goals is mathematical and mechanical basis. You should be familiar now with linear algebra, calculation of stress and strain, eigenvalues, and index notation. Ability to perform and interpret FEM. So this is what you need it for in your future careers, and knowledge about material behavior. So in a few minutes. Now, I will show you later an example of a silo and why the silo breaks. So that is the application example where we actually are doing research ourselves. My group is working on flow of material in silos or other systems. This is the mini silo, mini hourglass, where you can see that sometimes material is flowing, sometimes it's fluid-like flowing, sometimes it's stopping to flow and becomes solid-like. Okay, so this is what we are doing research on. We are developing these simulation tools and we compare them to experiments and we predict experiments and we help industry to improve their devices. Fluid and solid-like, the transition from fluid to solid we call unjamming, and from solid to fluid we call jamming. And that are phase transitions, so switches between different phases of matter. Okay, now in the solid phase, whether it's linear elastic or whether it's plastic, we normally look at stress strain curves. I will show you an application example at the end. So stress on the vertical, strain on the horizontal. We have a linear regime and the slope is the Young's modulus. When the linear regime ends, that's the point of yield. Then we possibly get nonlinear. And at point 4, if we return, we recover not all the strain which we put in. So there's a permanent plastic deformation in this uniaxial tension test. Okay, so that is solid stress strain for solids. This is, for example, different material behavior. A and B are two different materials. 3 is the ultimate failure point, and there are different regimes in between. So in the links which I gave you, you can read more details about those. For a fluid, the only evident first difference is that on the horizontal axis, it's not strain, but strain rate. So how fast am I deforming something? And the Newtonian fluid then will display behavior which shows the slope as viscosity. And non-Newtonian fluids are either shear thickening or shear thinning, or plastic, Bingham plastic. And this is what the powders which we are working on are also doing, something like this. Okay, this was the philosophy slide of what is continuum mechanics. You can split it up in solid mechanics and fluid mechanics, but actually most solids are not perfectly elastic, so then comes plasticity. Most fluids are not perfectly Newtonian, then comes non-Newtonian behavior, and plasticity and non-Newtonian behavior sometimes cannot be distinguished, and that's merged into rheology. That's a science by its own. Okay, so the goals of this course: you should be able now to understand linear small strain deformations, isotropic material behavior. Isotropic means direction independent, and be able to work with it and solve the questions we give you for the exam. The material, I just went through that, so I don't have to repeat this again. And this is for a reminder, the sections of the course, and introduction is what I'm doing now. Presentations and practice material, you should have practiced a few hours now. You have still a few more to come. Free online links, take a look at those before the exam. A few points you will get by just answering simple questions on those. The quiz on materials will tell you what to expect. Videos, you have seen those, and tutorials. Okay, now that's the goals of the course. Again, we should have achieved most of those. Now, I want to conclude with that what I'm doing when I teach particle technology. So particle technology has a part which I teach typically in 1 hour and a half, 20 minutes, half an hour, to remind everybody who is taking the advanced particle technology course about tensors. So I give you this one now, also to show you something of that what we are doing research on. but also to show you the summary of tensors and how you can do that in half an hour or 20 minutes. Okay, so first a few words about particles. Particles are different than normal matter, and this is an experimental picture here where you can look inside the particles and you can see stress. So you do this by doing photoelastic materials, and the photoelastic materials, when it's bright red, the shear stresses are high, and when it's bright dark blue, then there are no stresses, but there are particles. So these particles do not feel stresses, these particles feel a lot of stress, and actually these so-called force chains, they are the reasons why, one reason why silos fail so often, because these force chains are pushing on the walls and then the wall breaks. In the background, you see computer simulations. I don't want to talk too much about that. So our computer simulations can represent these force chains perfectly well. And this is non-spherical particles. Force chains are also there. Particles which feel no stress and particles which feel a lot of stress directly in their neighborhood. Okay, and this is not only like particles, this is like people. Some of us feel a lot of stress, some of us feel much less stress. When I have finished this lecture, that's my last lecture, then I will be much less stressed than I'm now. Okay, and this is one of the silo examples. This is the silo before it fails. This is a truck, so this is 4 meters, so the total thing is 40 or 50 meters high. And this cube here, this is the zoom-in picture to the cube. And yeah, there's a lot of particle material which was flowing. It should not have flown. Okay, now, flowing and not flowing. Linear elasticity is about solid. So a sand pile is also a solid. It keeps its shape for quite a long time. So that's solid-like behavior. Liquid is always flowing, and sand is doing something in between. Sometimes it's solid-like, sometimes it's liquid-like, particle technology. Okay, and yield stress is the resistance against flow at the point when it starts to flow. So that's one of the terminologies. Okay, now in a silo, you can have a filled silo. It can flow or it can jam. Arches are forming here, bridges are forming here, as you can see here. Okay, in a silo, when the material is flowing, it will flow with a certain velocity profile and it will flow out here. So this is a very old picture from a book on particle technology, how to design a silo. This is where my colleagues need for consulting the knowledge about stress, strain, deformation, and velocity gradients. This is the similar movie. I don't have to show this again. This is the similar movie as the hourglass, which I showed before. Go away. Okay, now tensors, crash course. This is now 10 minutes summary of what you should know about tensors. Think about their relation to fluid mechanics, hydrodynamics, solid mechanics, elasticity. This is the subject of this course. And plasticity is what materials most of the time are doing when you stress them too much. Tensors are also in magneto-electrodynamics, relativity theory, but that's beyond our reach. Now, tensors. Number one. I have 6 slides here to show you. Describe physical quantities, allow coordinate-independent formulation of physics. This is why we work with tensor. Examples for scalars: density, pressure, hydrostatic stress, pressure, energy, whatever. There are more. And we call this tensor of order 0, rank 0. Vectors: velocity, force, electric field, accelerations. These are all vectors, rank 1. Tensors, the unit tensor, stress, strain. And then there are higher order tensors, rank 4. Okay, now what is the number of tensor entries? And that is dimension to the power rank d to the power r. So in 2 dimensions, a scalar has 1 entry, 1 value. A tensor has 2, rank 2, and that means 4 entries. In 3D, scalar, vector, tensor, 9. That is the matrix which we are working with all the time. So this is how the counting, number counting. What is the meaning of a scalar? It's a direction-independent physical quantity. Okay, so hydrostatic pressure, it can be position-dependent, but it will be direction-independent. What is the meaning of a vector? It's a scalar quantity with a direction. So speed, for example, is the norm of the velocity, and the velocity itself is a vector. So speed times unit vector gives you the velocity vector. What is the meaning of a rank 2 tensor? Okay, so it's a physical vector quantity, vector-like quantity, but it has 3 magnitudes plus 3 directions, as we know from the eigenvalue analysis. So for example, stress. Okay, and I don't discuss what higher order tensors here. Now, you have seen this picture many times in different versions. When we talk about the stress cube, we want to see a coordinate system, we want to see the cube, we want to see the stress directions on the cube. And here, actually, the arrows are pointing inside. This is a different community. I want to show this to you once. Some communities are using the stress compressive positive. Then they are doing that what we did all the time. And if stress compression is negative, like in some solid mechanics books and so on, then the arrows are pointing in. So for the exam, either you have to describe which convention you are using or stick to ours, and then we will understand your answers better. Okay, so this is stress. In the eigensystem of stress, we have no shear stresses. That is why the cube, okay, it's rotated, but it's simpler because you don't have to plot all these shear stresses, only sigma 1, sigma 2, sigma 3, the eigenvalues, which are normal stresses in the 3 different directions. Okay, now this one I added for you in case you need it later. So calculate the stress eigenvalues, take the determinant, linear algebra, you get the characteristic equation. Sometimes that allows you to calculate the eigenvalues. Sometimes it's tricky because it's a third order polynomial. So in the examples, we have given you several cases. Now, if you go to the deviatoric stress, then actually you will see that the characteristic equation is becoming simpler because J1, the first invariant of the deviatoric stress, is by definition 0. So this term disappears, and you only have the second and the third invariant. Now, I found in one of my old East German, Russian translated math books a nice formula, which I also put in the MATLAB script on Canvas, which allows you to calculate arbitrary eigenvalues of this equation. So this is giving you 3 eigenvalues, S1, S2, S3 are the 3 eigenvalues. And we don't expect this from you to do it. We will give you solvable equations. But this one is also related to yield stress. So in your future career, if you work with solid mechanics, that is a handy calculation help. Now, back to the mathematics. I'm here using not the index notation, but symbolic notation. Sometimes I do that. Okay, so remember, if you take the stress tensor, add it transposed divided by 2, then you get the symmetric stress. What's the direction of the stress? Okay, and that is related to the eigenvalue calculation formula, which I just showed you, and to the eigenvector calculation formula, which you should have practiced meanwhile a few times already. So those are the directions, the 3 directions of stress. 3 eigenvalues, 3 directions. So the stress has a different meaning than a vector. A vector has only 1 direction. Oops, that was too fast. Okay, and the eigensystem, actually the eigensystem of the stress is the coordinate system where the tensor is diagonal. No shear stresses. That's what it means. I said that already, and that's the most important insight. Now, the tensors. How many independent entries has a symmetric stress? Okay, that's one of the questions you should be able to answer now. How many independent entries is different from the number counting before? Because then stress symmetry comes into play, and instead of 9 entries, we have only 6 in 3 dimensions. Okay, then you should be able to decompose the stress into its isotropic part. That's the direction independent hydrostatic stress or pressure. Some people abbreviate it just and say pressure. You should be able to get the deviatoric stress and the antisymmetric stress, which is related to couples and torques. We did not use it, and in mechanical equilibrium, this one disappears. But in general, it can be non-zero. You should be able, same way, decompose the deformation gradient into isotropic strain, deviatoric strain, and the antisymmetric, which is called vorticity. This is something which is important in hydrodynamics. Okay, and T is now any tensor. It could be stress or strain, and this is the equation. This is the isotropic direction independent part. We call it also volumetric part 1 is the unit tensor. This is the symmetric deviatoric part, and this is the antisymmetric part. So every tensor in 2 dimensions, rank 2, can be decomposed this way. Okay, forget about the antisymmetric one, and this is what we are working with all the time. The first 2 terms, isotropic and deviatoric symmetric. Okay, this is the saying the same thing again in decomposition rules. Trace of tensor is the first invariant divided by the dimension, and you get the isotropic contribution. Deviatoric, take the symmetric tensor, subtract the isotropic direction independent contribution, and you get the direction dependent contributions. And the antisymmetric stress, that one we don't need for this course. Okay, then when you have a stress tensor in a particular 2-dimensional stress state, so here in 1 and 3 direction, then you can plot the circle of Moore without any details given. The circle of Moore gives you all possible normal and shear stresses, sigma and tau, on an arbitrary orientation plane in your stress space, in your real space, sorry. Okay, and this is how the circle of Moore looks like. In geotechnique books, people are using P and Q. We were using M and R, middle point and radius. P is hydrostatic pressure. Q is the norm of the shear stress, one norm of the shear stress. Okay, and this Moore circle actually can be used in the design for silos. This is not what you need to know in the exam, but I want to tell you, silo design is one of the things where you need to know exactly these Moore circles, and you have to measure a material at high confining stress, at low confining stress, and you want to know what is the situation at the outlet of the silo such that the material still can flow. So if your shear stress is larger than the yield surface, the material will flow. If your shear stress is smaller inside the circle, then it will not flow. Okay, and this picture, the shear stress to normal stress picture, this is very much like friction. You take a slope, take a cube of material, put it on the slope, and this is force equilibrium for this cube. And if you tilt the slope further, the block of material will slide, so overcome friction resistance, and take the forces and divide them by the area, and then you get the stress strain picture. So if you forget about the stress strain definition and so on, think of this simple example. Take a cube with a certain area, it's touching the slope, and take the forces, divide them by the area, and then you get stress strain. We were talking most of the time about shear stresses and normal stresses, tau and sigma. There are also cohesive stresses, like due to glue or due to liquid or due to van der Waals adhesion, which are making the material stick together. That is an additional stress. I didn't mention that one so far, but that one is actually the reason why we have this yield stress behavior. Okay, so that was the end of the summary almost. And describe physical quantities. This is what tensors do. Direction-dependent one for non-Newtonian fluids and solids and rheology. You know now what is isotropic, deviatoric, micropolar. You don't have to know, but you should have heard about it. And the formulation of flow behavior for yield stress fluid. This is what we are actually doing research. This is advanced. This is beyond this course. Okay, now I show you one example, what in silo design we can do with this stress-strain relation. So you remember we did force equilibrium and we derived the stress equilibrium. In order to find out what is the stress in a silo, we use the force equilibrium or the stress equilibrium. So d sigma, dz. So the d sigma on the left-hand side, the dz on the right-hand side. This is the derivative of the stress, of the vertical stress in a silo. And this one is the force equilibrium equation or the stress equilibrium equation. And if you solve that, then you get that the vertical stress is looking like this. So the solid line here, this is how the vertical stress at the top of a silo, the stress must be 0, I mean atmospheric pressure. And when you go down in the silo and you have a liquid in the silo, then you would follow the straight line. The powder material in the silo, the straight line is bent over and it saturates here at this level. Okay, and when the silo is opened and the material starts to flow, then the stress is peaking very high extreme values. So you have to design your silo here very stable because the stress will be, in all situations of flow, very high here. So in your silo, you want to design it stable here. And most of the designs are using much less material when you go up, because you see the stress is not getting very high here. But if something is happening and one of these force changes is kicking the wall here, then the silo can fail. Okay, and that's the reason why silos fail. A silo with water would have to be getting continuously thicker when you go from top to bottom. Okay, and this picture here is the reason why silos are almost always tall and narrow, because that makes silos cheaper. You need less materials because you explore this decrease in stress. And that is why the oil tanks, when you go outside of Enschede, they are rather flat, few meters high only, not 40 meters high, because the hydrostatic pressure is going up linearly. So if you make it too high, you need too much material at the bottom. Okay, and the peak here is the reason why silos fail so often, too often. Okay, and this is now actually a way to plot the stress. The lines here are following the maximum principal stress, the maximum eigenvalue of stress, and in a configuration, you will see that the maximum principal stress is going down and towards the walls. And in the hopper, the maximum principal stress is actually going horizontal. And this one is the reason why the particles stop to flow and why you form these arches in the silo. Okay, we do computer simulations of silos. We do calculate all the continuum fields like density, displacement, momentum density, velocity gradient, and also stress inside the silo. So we can do all this from computer simulations, and many things we also can do experimentally and bring this together. Okay, so this is the end